All right, greetings, scholars. We're continuing our exploration on Chapter 5 on polynomial rational functions, and here we're going to be working on Section 5.5, zeros of polynomial functions. Oh, missing another slide, man. This one is all messed up. Well, missing my learning objectives, but that's okay. Let's see. So we have evaluating a polynomial using the remainder theorem. The remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is the value f of k. Okay, let's see this in action. Using the remainder theorem, evaluate this function at x equals 2. So we can actually use synthetic division here, right? So in this case, we put 2 in the chair. We take our coefficients. Notice the powers go 4, 3, 2, 1, 0. So every power is accounted for. So we can just take our coefficients, 6, -1, -15, 2, and -7. So then the remainder after we do synthetic division is going to be f of 2, right? So f of 2 is equal to the remainder. Okay. So remember, the first coefficient just comes down. On the diagonal, we multiply. So that's 12, 11, 22, 7, 14, 16, 32, 25. Okay. So because our remainder is 25, what we're saying is that f of 2 equals 25. Okay. So according to the factor theorem, k is a zero of f if and only if x minus k is a factor. So the factor theorem, like if when we do synthetic division or polynomial long division, if our remainder is 0, then x minus k is a factor of the original, right? So we can use synthetic division and polynomial long division when we as we factor. So we want to show that this linear binomial is a factor of this, okay? 3, 2, 1, 0, okay? And then use the factor to determine the zeros. So we want to verify that this is a factor, and then we want to find the zeros of this guy. So we're just going to do synthetic division. We're dividing by a linear binomial, so the 0 goes in the chair. The 0 in this case is going to be -2. And our coefficients are 1, -6, -1, and 30. We don't need a placeholder because every power is accounted for. The first term just comes down. Diagonal, we multiply, then we add, then we multiply, we add, we multiply, and then if we add, we get a remainder of 0. Okay. So we confirm that x plus 2 is indeed a factor. If we started with a degree 3, now at this point, the depressed equation is at a degree 2. Okay. So now what we have is x plus 2 times x squared minus 8x plus 15. All right. And we're going to factor that further. So the x plus 2 just comes down. We have x and x. We want to see if we can factor this trinomial. Now notice that the second sign is plus, so I know my two signs are the same. They're either both positive or both negative. Because the first sign is negative, that tells me the larger number is negative. So then we know that both signs are negative. Okay, 5 and 3. So this is a completely factored form of the original, and our zeros look like they are -2, 3, and 5. Okay. So the rational zero theorem states that if a polynomial has integer coefficients, then every rational zero of f of x has the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. Okay. So with the rational zero test, given a polynomial, we're going to do all combinations of the factors of our constant over the factors of our leading coefficient. And then if our polynomial has any rational zeros is going to be somewhere in this list. This list that we're going to generate, these are not the actual zeros. This is the list of all possible rational zeros. So again, if it has zero, any rational zeros, it's somewhere in that list. And we can use that list to kind of like find our zeros of our polynomial, right? Now this just says list of possible rational zeros. It doesn't say find the actual zeros, right? So this is a showcase of the rational zero test. So we're going to say our P over Q. That's not a Q. I don't know what it's right now. All right. Where the P are the factors of our constant term. So our constant in this case is -4. So the factors of -4, plus or minus 1, plus or minus 2, and then plus or minus 4. And then the factors of our leading coefficient being 2 is going to be plus or minus 1 and plus or minus 2. So then our list of possible rational zeros, we do all combinations with the blue divided by each of the red, right? So the list of possible rational zeros, plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus a half. Now we already have plus or minus 1 and we already have plus or minus 2. So what we're saying here, and let me kind of do this real quick. Okay, cool. This is exactly what I want. Okay. So what we're saying, let me see. So again, the P came from there and the Q comes from here. Okay, that's enough. So what we're saying is that if this polynomial has any rational zeros, it's somewhere in this list. Now, these are not the actual zeros, but, you know, if it has a rational zero somewhere in this list. Okay. So last over the first. And they got the same thing we got. So use the rational theorem to find the zeros here. So now we want to use the rational zero theorem to find the actual zero. So first we're going to generate that list of possible rational zeros. Again, where our P over our Q. I don't know why I'm struggling with these Q's today. So the factors of P are just plus or minus 1, and the leading coefficient is 2. So that's plus or minus 1 and plus or minus 2. Again, this one is just plus or minus 1. So the list of possible rational zeros look like it's plus or minus 1 or plus or minus a half. Okay, so we only got 4 possible rational zeros. So then from this list, we can use synthetic division. If we get a remainder of 0, then we know that that's a 0. I'm going to start off with 1. 3, 2, 1, 0. So every power is accounted for, so we don't need any placeholders. 2, 1, -4, and 1. Okay. The first term just comes down. Diagonal, we multiply, then we add, we multiply, we add, we multiply, and we get a remainder of 0, right? So that means that 1 is one of our zeros, okay? So then if we started with a degree 3, at this point we're now at a degree 2, okay? And I'll keep working over here. So if 1 is our 0, the factor takes on the form x minus 1, and we still have this 2x squared plus 3x minus 1. And then let's see if we can factor this, x and x. So because my second sign is negative, I know my two signs are the opposite. Because the first sign is positive, I know my larger is positive, right? So we have opposite signs. One's positive and one's negative. Nope. No, we got to back up. I think I'm gonna use factor by grouping. So let me back up here. Let's see. So because the leading coefficient is not 1, we have to say a times c. So that gives me a -2. The factors of -2 are, it looks like, maybe we don't have a rational 0 here. Yeah. Because it's going to be what, like 2 and -1, but those don't add to 3. So it looks like the only rational zero, let me make sure. We could do quadratic formula. Let me see, negative b, let me see, b squared minus 4ac, 9 minus or plus 8, yeah. So rational zeros, right? So if we try to factor that remaining quadratic, I think we get like a irrational zero. It's not rational. So we only get one rational zero here. Two, 1, -4, 1, 2, 2, 3, -1, -1, 0. Yeah, the only rational zero we get is the first one, x equals 1. I think we do get a 0 from the other one, but it's not rational. One is the only rational zero of this function. Yeah. Okay. Now what they did with that list, they took each of those possible rational zeros and they passed it through the function, and they only got 1 0 when x was 1. So I mean, that's another way to do it. Okay, that's fine. Okay, let's just kind of work an example. Find the zeros here. Okay, so let's start off with the rational zero test. If we did our p over our q, what color was I using before? Okay. All right. So let's start off with q. The leading coefficient is a 4. The factors are 4, plus or minus 1, plus or minus 2, and then plus or minus 4. The factors of our constant term is just plus or minus 1. So then the list of possible rational zeros, plus or minus 1, plus or minus a half, plus or minus a fourth or a quarter. Okay. So let's start off with just 1. That's a simple zero to test since it's in our list. Now notice every power is not accounted for, so we're going to need a placeholder. So then it's 4. Looks like the squared is skipped, so we need a placeholder there. 4, 0, 3, 2, then -3, and then -1. Right? We started with the degree 3, so we have 4 coefficients to account for. So we're looking good. The first coefficient just comes down. Diagonal, we multiply, we add, we multiply, we add, we multiply, and it looks like we found a 0. Okay. So then if we started with the degree 3, at this point now it's a degree 2. All right. Let me see if we can factor this guy. All right, so basically what I was doing, again, because my leading coefficient is not 1. Now we could just test the remaining rational zeros, but we have 6 of them. So I just prefer to factor, because we got it down to a quadratic. We could either use quadratic formula or complete in a square or just factor it. Like I'm going to use AC method. And so what I was doing, I was rewriting this middle term. I was looking for 2 numbers that multiplied to give me a times c, and added to give me the middle term. So 2x and 2x, I think, works. So then what we're going to do, in the upper left-hand corner goes the 4x squared. The bottom right goes our constant. And then on the off diagonal, we rewrite the middle term using the 2 numbers we just found, was 2x and 2x. Okay. So then now we can factor, right? If we look at the 2 on the top, what can we factor out of the 2 on the top? We can factor out, looks like a 2x. What do the two on the bottom have in common? Just 1. The 2 on the left, it looks like we can factor out a 2x. And the 2 on the right, it looks like it's also just plus 1. Okay. And I guess I'll finish working over here. So we found a 0, which was 1. So then that takes on the form of x minus 1. And then it looks like we have this 2x plus 1 squared, right? So then in this form, our zeros take on the form of what? Negative 1/2 and 1. It looks like these are our rational zeros. And we can confirm that the negative 1/2 is a 0. If we do synthetic division, the remainder should be 0. Okay, and it looks like the negative 1/2 has a multiplicity of 2. It occurs twice. I don't know what my table is like. I'm trying to get it to be quiet, but it's just like if I make any kind of move or touch it, it just making all this noise. Okay. So dividing by x minus 1 gives a remainder of 0. So 1 is a 0. The quadratic is a perfect square. It can be written as this form. So then the zeros of the function are 1 and negative 1/2. And a negative 1/2 has a multiplicity of 2. And that comes from like the power, because we had that 2x plus 1 squared. That's why the negative 1/2 has a multiplicity of 2. Right? And so what that means, because it has an even multiplicity, it's going to bounce off the x-axis. All right? So here's the negative 1/2. It bounces off the x-axis. X equals 1 had an odd multiplicity, so it crossed. So the fundamental theorem of algebra states that if f of x is a polynomial of degree n strictly greater than 0, then f of x has at least one complex 0, and we can write this theorem to argue that if f of x is a polynomial of degree n greater than 0 and a is a non-zero real number, then f of x has exactly n linear factors. Okay. Where these c's are complex numbers, therefore f of x has n roots if we allow for multiplicities. Does every polynomial have at least one imaginary 0? I guess it boils down to if you count like 0i, like 0 times I, is that considered imaginary? I don't think so. Right? Real numbers are subsets of complex number, but not the other way around. A complex number is not necessarily imaginary. Real numbers are also complex numbers, all right? Yeah. So find the zeros of this polynomial function. Now, because they just said that part on imaginary, I'm like, well, are we going to consider imaginary zeros now? But I don't know that we've talked about that yet. So let's start off with the rational zero test, where we do our P over Q. So the factors of our constant term are plus or minus 1 and plus or minus 3. The factors of our leading coefficient, the same thing. Okay. So then our list of possible rational zeros. Okay. And then a third. I think it's the last one. Okay. So again, 1 is just a good one to start with. It doesn't always work, but it's just a simple one to start. So then let me see, 3, 2, every power is accounted for, so we don't need any placeholders. 3, 9, 1, 3. Again, the 3 just comes down. 3, what is that, 12? That makes 13, that's not a 0, right? So that's not a 0. I guess let's try, let's try, honestly, looks like we can factor this guy. Like if we do factor by grouping in the beginning. Let me think. Looks like -3. Let me try, because when I do factor by grouping, it looks like I'm getting a common linear binomial term of x plus 3. which implies that negative 3 is a 0. So I'm gonna try confirm that negative 3 is one of our zeros. So we say 3, 9, 1, 3. The 3 comes down. That's a negative 9. That's 0, 0, 1. Negative 3 is indeed a 0. Right. So now, obviously, on your end, we tried 1. You might try negative 1, and then 3, and then negative 3. You could look at the graph, look at the chart, just to find that first 0. A lot of times with these, the hardest one is finding that first 0. Once you find that first 0, then it kind of flows from there. So we started with degree 3. At this point, it's now a degree 2. Okay. Can that be factored? Let's see, subtract and divide. It's not rational. With complex zeros, okay. Okay. So if negative 3 is our 0, the factor takes on the form x plus 3. And we have this 3x squared plus 1 remaining. Right? And I'll keep working over here. So we're trying to find a 0 from that second binomial term. What I'm going to do is just set that to 0 by itself. I'm going to isolate that guy. I'll do it in orange, I guess. We got this 3x squared plus 1 equal to 0. If I subtract, we get 3x squared equals negative 1. Then I divide. And then I take the square root. X equals plus or minus the square root of a negative 1/3. Right? So the square root of negative 1 is going to be I. Plus or minus I. Now I think we can leave it as 1/3. Normally we don't leave it as that. Like usually we would rationalize that. It would become the square root of 3/3. But sometimes the text, they don't always rationalize it. Right? But again, the square root of negative 1 is I. So we just put it in front of the radical. So then our zeros look like they are x equals, I think we got negative 3. Let's clean it up. Negative 3, and then plus or minus I times the square root of 1/3. And again, they might rationalize that guy. Paste. That's good about like that. I'm just going to move this just a little bit. Yeah, like there is good. So we got negative 3 and plus or minus I times the square root of 1/3. Yeah, so they did rationalize it. Square root of 3/3 is fine. Okay. Sorry, my table is just... Okay. Oh my God, it's driving me nuts. Is it this thing? Is it this? Sorry, I'm trying to figure out like what's the culprit, like that just needs... Is it this? Something just needs like a little bit of like WD-40. It's driving me nuts. Let me see if I come like around here. Let's see if this is a little bit better. Nope. It's driving me nuts. Oh my goodness, will you please stop? All right, so using the linear factorization theorem to find polynomials with given zeros. According to the linear factorization theorem, a polynomial function will have the same number of factors as its degree, and each factor will take on the form x minus c, where c is a complex number. Okay. If a polynomial function has real coefficients and complex zeros in the form of a plus bi, then the complex conjugate of the zero a minus bi is also a 0. Right? So whenever we have one complex zero in the form of a plus bi, its complex conjugate is also a 0. Essentially, that's what it's saying. Find a 4th degree polynomial with real coefficients that has these zeros, has the zeros of negative 3, 2, and I, such that f of negative 2 is 0. Okay. And so because I is a 0, negative I is also a 0. And if we take these 0, the factors are going to take on the form of x minus 0. Right? So we're going to find some polynomial function. We're going to say some a times. Now x minus -3 becomes x plus 3, x minus 2. And then it looks like it's x minus I and x plus I. Okay. Okay, so let's expand this out. Let's see. So if we follow that first one, x squared plus x minus 6. If we follow the second two, x squared outer and inner cancel, and last is minus I squared. I squared is -1, so that's plus 1. Then we need to expand that. Let me see. X to the 4, x squared. No, that's not working. No, what did I hit? Oh no. Oh, where'd it go? There it is. Let me see. Okay, we'll do this. So let me see. That's x to the 4, x cubed, 6x squared, and then repeat everything. X squared plus x minus 6. Okay. Combine like terms. X to the 4, x cubed, minus 5x squared plus x minus 6. And then if we let, when x is -2, y is 100. Let me duplicate this side. Again, when x is -2, y is 100. So then we'll have a times, let me see. So that's going to be what, 16 minus 8 minus 20 minus 2 minus 6 equals 100. Let me see. That's an 8. That's -12, -14, -20. So -20a equals 100. So then a equals, what is that, a -5? So then it looks like our f of x takes on the form, if we distribute a -5, -5 x to the 4 minus 5x cubed plus 25x squared minus 5x plus 30. Okay. So it should be the case when we let x be -2, we should get 100. Yeah, I'm just going to kind of go with it. Let's see. I think what we have is good. We're not too far off. Okay, so now we have Descartes rule of signs. According to Descartes rule of signs, if we let f of x be a polynomial with real coefficients, the number of positive real zeros is either equal to the number of sign changes of f or less than that by an even integer, and the number of negatives zeros is going to be the number of sign changes of f of x or less than that by an even integer. Okay. So again, that to me is just easier to see in action. Use the Descartes rule of signs to determine the possible number of positive and negative zeros. So if our f of x, negative x to the 4 minus 3x cubed, 6x squared minus 4x minus 12, we want to count the sign changes. So there's 1 there, 2 sign changes. So then possible positive, we either have what 2 or 0 zeros, positive zeros. Okay. And then for the possible number of negative zeros, we got to consider f of negative x. Let's see. So that first one stays as is. That sign changes. That one stays as is. That sign changes. And that one stays, right? So we got 1, 2, right? So then possible number of negative zeros, it looks like it's also 2 or 0. Negative zeros. Okay. Okay. So again, we could have either two positive 0, 2 or 0 for each. And again, the total zeros in this case have to total up to 4, especially if we consider complex zeros. So we could have 2 positive and 2 negative, and then 0 complex, or 2 positive and 0 negative and 2 complex to give us a total of 4 zeros. And so these are all the combinations of like 2, 0, and 4 that we can do with positive zeros, negative zeros, and complex zeros. The main takeaway here is that the total zeros are 4, right, in each case. This might be the last one. A new bakery offers decorated multicolored, multi-tiered cakes for display and cutting at quinceañera and wedding celebrations, as well as sheet cakes to serve most of the guests. The bakery wants to make the volume of a small sheet cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake, and the height of the cake to be 1/3 of the width. What should the dimensions of the cake be? Okay. So it sounds like we're working with a rectangle. I guess we'll do this color. So copy, or rectangular prism. Okay. The volume. Okay, so we're given, they want the volume to be 351 cubic inches, so inches cubed. Okay. A rectangular solid, a rectangular prism. They want the length of the cake to be 4 inches longer than the width. So the length is the width plus 4. The height of the cake to be 1/3 of the width. So the height is W/3. Okay, so the volume is going to be the length times the width times the height. So the length is what? Let's kind of keep working here. The length is W plus 4. The width is just W. And the height is W over 3. And that needs to equal 351. So we have one equation, one unknown, so we can solve. To clear out the fraction, I'm gonna multiply the left and the right by 3. Let me think about this. Okay. So if I multiply this by 3, right, I'm going to say that this is going to cancel this. Am I doing this right? Yeah, this is fine. Okay. And I'm going to distribute a W squared into the parentheses, all right, because it's going to be W times W. So if we distribute a W squared, that's going to give us W cubed plus 4W squared. Okay, and I'm going to go ahead and set it to 0. So minus, Siri, what's 351 times 3?
351 times 3 is 1053.
Siri, repeat that result.
351 times 3 is 1053.
Okay. Uh-oh, okay. Okay, equals 0. Oh, 1053. 351, let me see. 5 and 3 is 8, 9, so that is divisible by 3. We could use the rational zero test. I mean, we could do the possible number of positive zeros. Let me see. There's only one sign change, so there's only one possible positive zero from Descartes rule of signs. If we do the rational zero test, we would have to do the factors of 1053. Let's list out the factors of 1053. Okay, so we got 3 times 351. Let me see. 351. 117. Okay. So looks like we have 3 times 3. Now 117. Siri, what's 117 divided by 3?
117 divided by 3 is 39.
And then 39 divided by 3 is 13. So it looks like it's 81 times 13. Siri, what's 81 times 13?
81 times 13 is 1053.
Okay. So if we did the rational, now I feel like with something like this, I mean, we could do the rational zero test and then test all those possible rational zeros. I'm tempted to just look at the graph just to quickly find that 0. All right. Let me think. I know I probably should show this on the screen. I'm just going to look at the graph. So on a separate device, I guess I can do it here. It's not a big deal. Let's just close all this out. This one. Okay, so now we have this W cubed so we're going to say x to the power of 3. Again, the hardest part is finding that first 0. 4x squared minus 1053. Okay. I'm just going to look at the standard graph and see if it's a simple 0. Like if it crosses, I'm anticipating, there it is. It looks like when x is 9. Right? So now I'm just going to verify that when x is 9, that gives us our 0. I think that's it, because we only anticipated one possible positive 0. So it looks like the width should be 9 because of Descartes rule of signs, right? We only had one sign change. So it looks like, let me see, length. Yeah, let's do, like, the width is 9 inches. So that means the length would have to be 13 inches. And the height would have to be 3 inches. Siri, what's 9 times 13 times 3?
9 times 13 times 3 is 351.
Okay, so I think that's exactly what we wanted. Okay, so again, I just avoided, like, I did do the Descartes rule of signs. I just did it quick. Again, with the Descartes rule of signs, we count the number of sign changes, right? So if this is my f of w or whatever, or my v of w, we only had one sign change. So that tells us that we have one possible positive rational 0, right? So I'm not sure if it's rational or not. Let me see something. It's not necessarily rational, but it's positive, right? So the Descartes rule of signs tells us, because after the Descartes rule of signs, we had one possible positive 0. And then we found that 0 just by looking at the graph. When I glanced at the graph, I saw it cross the x-axis at 9. So then I was like, okay, well, let me confirm that when x is 9, it makes, it's actually, the output is 0, right? And it was. And then, again, we were only looking for one possible 0, so we just went with that one. So that's how we got this. 9, 13, and 3. Let's see, how do we do? Right, we just didn't write all that out. Nine, 13, and 3. Yeah, 9 by 13 by 3. Yeah. Okay. So that was an adventure. Let's kind of investigate the way the book did it. So I think they started out similar to what we did. Length times width times the height. We got that same thing. And then they want the volume to equal 351. So then they created one equation and one unknown. They set it to 0 and solved. Descartes rule of signs tells us that there is one positive solution. The rational 0 theorem tells us that the possible rational zeros. Now that's what we just didn't write out because I just didn't feel like doing all of it. We had it factored though, like the 1053. Where you see the purple is the 81 times 3, and then we had to do all the plus or minus 1, 3, 9, 13. I wasn't about to write all that. All right. And then only positive numbers make sense as a dimension for a cake, so we don't need to test any of the negative values. And then let's begin by testing the values that make the most sense as the dimension for a small sheet cake. Use synthetic division to check x equals 1. So when they got 1, they didn't get a 0. 3, they didn't get a 0. And then when they hit 9. Now, again, I just glanced at the graph. We got lucky that the 0 was less than 10. If it were not less than 10, I would need to zoom out to get a better view of the graph. But once we found that 0 and we confirmed that it was indeed a 0, then that was our result. So they essentially did the same thing. They did a little bit different, but yeah. Okay. And so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.